entropy is often described as disorder, but that word is too small and too careless for what it truly represents. Entropy is a count, a measure of how many possible microscopic arrangements sit beneath the smooth surface of the world we experience. It is the quiet census of the unseen. Imagine a simple cup of warm water. To your eyes it looks uniform and calm, yet inside it countless molecules dance in restless motion. They collide, rebound, and trade energy in ways that no human mind could ever track one by one. Each specific arrangement of these molecules is called a microstate. You never see these microstates directly, but you feel their collective behavior in the warmth of the cup, in the ease with which heat seeps into your fingertips. Entropy measures how many of these microstates are available, how many fine-grained patterns can exist beneath the same calm surface we call a macrostate. The reason this matters so deeply is that physics at the smallest scales does not tell the universe which microstate to choose. The universe is free to explore them, and when there are many more microstates corresponding to what we call disorder than to what we call order, the universe drifts naturally into that larger space. It is not pushed, it simply follows the overwhelming statistical weight of possibility. A pristine crystal has relatively few microscopic configurations. A shattered crystal has far more ways for its pieces to be arranged. In this simple idea lies the secret of why entropy increases with time, why ice melts, why coffee cools, and why a dropped egg never reassembles itself. If we filmed an egg falling from a counter and breaking on the floor, then played the film in reverse, the reversed motion would still obey the microscopic laws of physics. But it would look absurd. Not because the laws forbid it, but because the number of microstates aligned with the intact egg is tiny compared with the vast range of microstates allowed once the shell has scattered into countless fragments. To go backward would require an extraordinary conspiracy of motions. Each fragment must move in a very precise path that returns it to its original smooth shape. Such a path is not impossible in a strict mathematical sense, but it is fantastically improbable. This is the origin of the arrow of time. It emerges not from the laws themselves, which run equally well forward or backward, but from the statistics of large numbers of particles. Time, as humans experience it, is deeply tied to entropy. The past is the collection of states where entropy was lower. The future is the space where entropy is higher. We move toward the direction with more available microstates, and the universe does the same. This is why memories form in only one direction. It is why stars burn their fuel instead of gathering it back into pristine reservoirs. It is why life grows older and does not revert to youth. Entropy gives direction to existence itself, an invisible guide that dictates what can unfold naturally and what would require an impossible coordination of events. In a more profound sense, entropy is a measure of lost information. Not lost in the absolute sense, because the microscopic details still exist, but lost to us. When cream mixes into coffee, the precise paths taken by each swirl of fluid become too intricate to reconstruct. The information that once described those paths becomes scrambled, hidden in layers of complexity too fine to recover. Entropy is the price we pay for not being able to track every detail of the universe. It reflects our coarse understanding, our smoothing over the countless nuances of motion that define reality at the smallest level. This view carries a quiet consequence. If we could somehow reduce entropy across the universe, we would be attempting not just to decrease disorder, but to reverse the flow of time itself. We would be asking the universe to choose microstates from a far smaller set, requiring an alignment of details beyond comprehension. We would be asking every molecule of air to reverse direction, every atom of matter to move precisely as it once did, every memory to unravel. Reducing entropy is not merely tidying up a messy room, it is attempting to make the past reappear. The link between entropy and time is so tight that if you imagine time as a river, entropy is the slope that defines its direction. Without that slope, the river would have no preferred path. Events could unfold forward or backward with equal ease. But because the slope exists, because entropy tends to rise, The river flows in only one direction and drags everything with it. Stars evolve, mountains erode, living beings grow and age. Even the expansion of the cosmos is shaped by this steady increase in microscopic possibilities. Yet entropy is not the only arrow shaping the universe. Gravity draws matter together, carving structures out of the cosmic sea. It builds stars, planets, and galaxies, binding them into forms that persist across billions of years. Gravity has its own direction of evolution. A cloud of gas tends to collapse inward rather than disperse outward. A star tends to fuse lighter elements into heavier ones, gradually altering its own structure. This gravitational arrow complements entropy, for the collapse of matter into dense structures releases energy that increases entropy around them. Stars shine because gravity compresses them. Black holes devour matter and hide their complexity behind horizons, increasing entropy in ways that push the boundaries of theoretical physics. The arrow of entropy and the arrow of gravity work together in our universe, each reinforcing the other. One measures the hidden possibilities of microscopic motion. The other sculpts the macroscopic architecture of everything we see. If entropy defines time, gravity defines structure. And together, they guide the story of cosmic evolution from the earliest moments to the far future. But because they are both so deeply woven into the nature of reality, imagining them running backward is not a simple act of inversion. It is an act of unmaking. If entropy were to reverse, time would lose its orientation. If gravity were to repel instead of attract, structure would dissolve. Before we reach the extreme case where both arrows fail, we must understand each arrow separately, beginning with the subtle and all-important rise of entropy. Entropy shapes not only physical processes, but also the very logic by which events make sense. You remember the past because the neural patterns in your brain have shifted from a state of lower entropy to a state of higher entropy. The act of storing a memory is a physical transformation that increases the number of accessible microstates in your brain. To remember something is to leave an imprint, and imprints require energy. They raise disorder. This means memory is never neutral. It is always tied to the forward march of time. If entropy were to decrease, memories would not simply fade. They would run backward. A person would not forget events because they are distant, but because the future requires those events to unravel. Memory is an emergent feature of the thermodynamic arrow. Consider a block of ice sitting at room temperature. The warm air around it carries more energetic microstates than the ice itself. Heat flows from the warmer region to the colder region because there are more ways for energy to spread out than to remain confined. In principle, the energy could all return to the block of ice, making it refreeze, but this would require the surrounding air molecules to coordinate in an unfathomably precise way. They would have to give up just the right amounts of kinetic energy at just the right times. Such coordination is allowed by the equations, but forbidden by common sense. It is as if the universe offers an infinite number of ways for disorder to grow, but only a handful of ways for order to return. This imbalance defines our experience of time more strongly than the ticking of any clock. Even stars follow this logic. A star burns because nuclear fusion yields states with higher entropy. Hydrogen fuses into helium, and in the process, energy is released into space. That energy spreads out, increasing the entropy of the cosmos. The star itself is a temporary oasis of structure, held together by gravity. But the moment it formed, the entropy of the surrounding region increased due to the release of gravitational binding energy. Gravity builds complex forms, but it does not escape the rule that entropy must rise. In fact, gravity accelerates this rise over cosmic time. When you step back and view the universe through this thermodynamic lens, you see that time is not a fundamental ingredient of the equations. It is a consequence of overwhelming statistical tendencies. If we could zoom in far enough, down to the quantum details, we would find that the equations run equally well forward and backward. Particles do not know or care which side of time they inhabit. They simply follow the rules, and the rules permit symmetry. The asymmetry comes from the fact that the universe began in a state of extraordinarily low entropy. Out of all the possible arrangements the early cosmos could have taken, it started in one of the tiniest pockets of order. This is a cosmic puzzle still not fully solved, for the early universe was hot and dense, yet smooth and simple. The smoothness means it had very few possible microstates. Its evolution since then can be seen as a long climb toward ever greater multiplicity. As the universe expands, space stretches and cools, but entropy still increases. Photons scatter, structures form and dissolve, matter clumps under gravity, and black holes grow. Each process unlocks new microstates that were not accessible before. The ultimate fate of the cosmos might be a featureless expanse where all energy is evenly distributed. In such a state, nothing meaningful could happen. Without gradients, there is no flow. Without flow, there is no change. Entropy would stand at its maximum, and time would lose significance. This journey from a low entropy beginning to a high entropy future defines the large-scale narrative of existence. Life emerges not in spite of entropy, but because of it. Living organisms are able to create pockets of local order by exporting entropy into their surroundings. A plant gathers energy from sunlight and builds complex molecules, but in doing so, it releases heat into the environment. The local decrease in entropy is always paid for by a larger increase elsewhere. The balance is never violated. Entropy is the accountant of the universe, and the books must always reconcile. The subtlety of entropy often leads people to view it as a destructive force, but that interpretation is incomplete. Entropy does not destroy structure. It governs how structure changes. It defines what is easy and what is nearly impossible. A snowflake forming from vapor is a process that lowers entropy locally, yet it occurs naturally because the molecules release heat into the surrounding air, increasing the entropy of the environment. Order can appear spontaneously, but only when the total entropy of the system and its surroundings still rises. This is why entropy is not simply a measure of disorder, but a measure of likelihood. High entropy states dominate because there are so many of them. Low entropy states are rare not because they are forbidden, but because they occupy an incredibly small volume of possibility space. When you step outside on a windy day, the patterns in the clouds, the swirl of dust, the turbulence of the air, all reflect the statistical dominance of these high entropy configurations. Nature selects them not deliberately, but inevitably. Viewed through this lens, the arrow of time becomes an emergent property. It arises from the imbalance between the number of possible past states and the number of possible future states. The past is the set of configurations that the universe has already passed through, constrained by the lower entropy boundary condition. The future is the vast ocean of configurations it has not yet explored. The universe drifts into that ocean because that is where most of the possibilities lie. Entropy makes the present a constantly unfolding frontier. Every moment is shaped by the tension between the simplicity of the past and the multiplicity of the future. This tension is also the reason that reversing entropy is such an extraordinary concept. To reverse entropy is to ask the universe to move into a smaller space of possibilities. It is to demand alignment where chaos normally reigns. It would require every particle in existence to cooperate with a precision that surpasses any miracle ever imagined. Before we imagine such an inversion, we must understand the other great arrow that shapes cosmic history. Gravity is the architect of structure. It pulls matter together, ignites stars, sculpts galaxies, and governs the largest motions of the cosmos. Gravity does not oppose entropy. It complements it. The collapse of matter into concentrated forms releases energy and increases entropy in the surrounding medium. Gravity and entropy move in concert, each reinforcing the other in guiding the universe toward complexity and then eventually toward dispersal. To appreciate what reversing entropy would truly mean, we must first examine gravity itself. Gravity enters the story as soon as matter exists, and its influence grows with scale. It is the only force that becomes stronger in collective form. A single grain of dust has almost no gravitational pull, yet countless grains together begin to attract one another. Over cosmic time, this gentle pull becomes the sculptor of everything visible. Clouds of gas drift through space, barely disturbed, until a slight density fluctuation gives gravity something to work with. Once matter clumps a little, the pull strengthens. More matter drifts inward. The clump grows. Heat builds as particles collide. The cloud contracts into a sphere. And after enough compression, nuclear fusion ignites. A star is born, not through violent command, but through slow and steady gravitational persuasion. From this perspective, gravity shapes the universe not through forceful blows, but through patient inevitability. It draws matter together because there are more ways for matter to clump than to spread perfectly evenly. Gravity thrives on asymmetry. A region slightly denser than its surroundings becomes denser still because the pull is stronger there. Over billions of years, these small seeds become galaxies whose arms rotate like vast whirlpools of light. Inside these galaxies, stars orbit in graceful patterns, while planets form from swirling disks of dust and gas. Everything we think of as structure owes its form to gravity and to the energy released as matter collapses inward. Yet gravity also plays a deeper thermodynamic role. When matter falls into a gravitational well, it sheds energy. That energy usually appears as heat or radiation, which escapes into space. This is a process that raises entropy. A gas cloud collapsing into a star becomes more ordered in a local sense, but only because it has expelled more disorder into its surroundings. The region around the forming star becomes a bath of photons carrying away entropy. This is the same pattern seen in all self-organizing processes. Local order rides on the back of global disorder. Gravity does not oppose entropy. It accelerates it by creating situations where energy can be dispersed more efficiently. Black holes represent the most extreme example of this relationship. When matter collapses beyond a certain density, gravity becomes irresistible. The matter disappears behind an event horizon, a boundary from which nothing can return. According to theoretical breakthroughs, black holes possess entropy of their own, proportional to the area of their horizons. This entropy is immense. A black hole is a master container of microscopic possibilities, far beyond anything that the collapsed matter inside could have produced in ordinary form. In this sense, gravity creates some of the highest entropy objects in the universe. It deepens the future and ensures that the arrow of time cannot be reversed on any macroscopic scale. Understanding this connection clarifies why imagining reversed gravity places us on unstable conceptual ground. If gravity were not attractive but repulsive, matter would tend to spread instead of gather. The formation of stars would never occur. The shaping of galaxies would be impossible. Black holes could not form at all. Even the earliest stages of cosmic evolution would unfold differently. Instead of tiny fluctuations growing into the cosmic web of clusters and filaments, they would be pushed apart. In a universe with repulsive gravity, structure would struggle to survive, much less flourish. But we are not yet ready to speculate on reversed gravity. First, we must close our exploration of entropy. Its rise defines time. Its increase shapes every natural process, from the cooling of tea to the birth of stars. Without it, cause and effect would lose meaning. Memory would dissolve. Motion would be unanchored. The world would become a sequence of events with no preferred order. And yet, entropy does not act alone. Gravity provides the architecture within which entropy unfolds. These two arrows, one statistical and one structural, work together to create the universe we inhabit. When we ask what it would mean to reverse entropy, we confront the limits of probability itself. Imagine every molecule of the atmosphere arranging itself into a perfect gradient. Imagine every photon traveling in precisely the right direction to reconstruct a past state. Imagine the entire history of the cosmos returning to a moment of pristine order, not because laws require it, but because everything happens with immaculate coordination. That is the essence of entropy reversal. It is not a simple running of the cosmic film backward. It is a demand that every microscopic detail obey a choreography of impossible precision. This thought experiment becomes even more challenging when we remember that entropy rises, not only because of molecular motions, but because of information. When you lose track of microscopic details, entropy grows. When information becomes scrambled beyond recovery, entropy grows. In the deepest sense, entropy is tied to what can be known. A universe with decreasing entropy would be one in which information becomes more accessible over time, one in which details sharpen instead of blur. Events would become more specific as time progresses, not less. The future would be more constrained than the past. The very logic of prediction would be inverted. This would have extraordinary implications for consciousness. Minds operate by forming memories, which depend on the irreversible increase of entropy. To imagine a conscious brain in a universe where entropy decreases is to imagine a brain that forms memories of the future rather than the past. Such a mind would not experience cause followed by effect. It would experience the unraveling of outcomes into their origins. Decision-making would be meaningless because the choice would already be encoded in the future state that the universe is converging toward. Free will would not simply vanish, it would reverse direction. All of these consequences stem from the simple fact that entropy shapes time. In our universe, the direction of increasing entropy and the direction of time are the same. If we tamper with entropy, we tamper with time itself. Before venturing into the speculative and dangerous territory of reversing entropy, we must tighten our understanding of gravity, for the two arrows of the universe are not independent. They lean on each other, they guide each other, and if one were to fail, the other would inevitably follow. This chapter has framed entropy as more than a measure of disorder, portraying it as the mathematical engine behind the unfolding of reality. The next chapter will explore gravity, the sculptor that gives the universe form. Only by understanding how these two arrows work in harmony can we grasp what it would mean to turn them backward. Gravity begins as a whisper, a force so faint that 2 grains of dust can ignore it for an eternity. Yet give gravity time, give it distance, give it mass, and that whisper becomes the architect of everything with shape and presence. Gravity is the reason the night sky is not a silent fog of drifting particles, but a grand arrangement of stars, spirals, clusters, and blazing cores. It is the patient sculptor that gathers scattered atoms into luminous spheres. It is the quiet engineer behind every world that has ever harbored oceans or mountains or living beings who ponder their own origins. To understand this force, you must begin with its most essential trait. Gravity is universal. Every particle with mass acts upon every other particle, no matter how far apart they may drift. While other forces weaken or cancel or operate only in specific contexts, gravity reaches across the cosmos without hesitation. In the earliest eras of the universe, when matter was still a hot and nearly uniform haze, tiny fluctuations in density gave gravity something to work with. A slightly denser pocket would attract more matter. That accumulation made the region even denser still, and the cycle grew. What begins as a minor imperfection in the smooth canvas of the cosmos becomes the seed of a galaxy. The collapse of a gas cloud under its own gravity is not a sudden event. It unfolds slowly, resisting with thermal pressure, shifting under turbulence, and losing energy with each collision of particles. But over millions of years, the cloud contracts, the center grows hotter, and eventually conditions cross a threshold so extreme that hydrogen fuses into helium, light appears, heat pours outward, a star is born. From here, the landscape of worlds begins to emerge. Dust grains orbit the infant star, clumping into pebbles. Pebbles grow into bodies the size of mountains. Mountains merge into protoplanets. The process continues until entire worlds form, each carrying its own potential for oceans, continents, and atmospheres. Gravity not only forms stars, it shapes their fates. A star is a delicate balancing act between the outward pressure of fusion and the inward pull of gravity. As hydrogen is consumed, the balance shifts, the core contracts, new reactions ignite, the structure reshapes itself. Eventually, every star runs out of fuel and gravity claims victory. What follows depends on the mass. A small star may puff off its outer layers and leave behind a white dwarf, a dense ember where matter is packed tighter than anything on Earth. A massive star may collapse violently, triggering a supernova so bright that it outshines its host galaxy for a moment. In that collapse, the core can compress past every known threshold and become a black hole, where gravity draws space and time inward like a curtain folding upon itself. In each stage of stellar evolution, energy is released. That release spreads outward as heat and light, and once again entropy increases. When a star collapses, the gravitational binding energy that is shed as radiation raises the entropy of the surrounding universe. This relationship is fundamental. Gravity creates structure by driving matter inward, but in doing so, it pushes entropy outward. The rise of structure and the rise of entropy are not competing outcomes. They are complementary expressions of the same thermodynamic reality. This interplay becomes even clearer when we examine galaxies. A galaxy is not simply a collection of stars orbiting a common center. It is a dynamic ecosystem where gravity guides patterns on scales far larger than any individual light. Spiral galaxies, with arms unfurling like cosmic storms, form because stars and gas settle into stable rotating structures shaped by gravitational resonances. Elliptical galaxies form through collisions, where two or more galaxies merge into a single larger whole. Even these catastrophic interactions obey the same rule. The merger triggers waves of star formation, heats gas, and sends radiation into space. Entropy climbs. Order appears not as a contradiction of entropy, but as a companion to its rise. The true power of gravity is that it does not saturate. It does not weaken when systems grow larger. It accumulates. A black hole with the mass of many suns exerts such a potent pull that not even light can escape from the boundary it creates. This boundary, called the event horizon, hides the interior from observers. Yet theoretical work has revealed that black holes possess a form of entropy that is astonishingly large. In fact, a black hole carries more entropy than the same amount of matter spread out in any other form. This is why black holes dominate the thermodynamic landscape of cosmic evolution. They are the ultimate containers of microstates, suggesting that gravity has an intimate connection to information itself. This insight reshaped our understanding of the universe. If entropy is a measure of hidden information, and black holes contain the most entropy of all known objects, then gravity is not merely a structural force, but a force deeply linked to the informational fabric of reality. The warp of space created by gravity does more than bend trajectories. It influences how information is stored, hidden, or revealed. Information that falls into a black hole becomes encoded in ways that challenge our most basic intuition. It is still present in some form, but inaccessible. The rise of entropy in such processes shows that gravity is a participant in the thermodynamic flow of time, not just a bystander. Yet for all its grandeur, gravity begins with simplicity. It is the natural result of mass curving the geometry of space. Objects follow the straightest possible paths within that curved geometry. A planet orbiting a star is simply trying to move in a straight line through a curved space. A star falling into a black hole is doing the same. Even photons feel this curvature, which is why they can bend around massive objects. Gravity sculpts the cosmos not by pushing or pulling in a literal sense, but by shaping the stage on which everything moves. Because gravity builds structure, it becomes one of the fundamental arrows of the universe. Left to itself, matter will clump, collapse, and concentrate. If this arrow were ever reversed, the consequences would be cosmic in scale. Every structure that gravity painstakingly assembled over billions of years would begin to come apart. But before we explore that radical inversion, we must fully understand gravity as it operates in our world. Its partnership with entropy guides the entire evolution of the universe. Its steady pull allows stars to shine and planets to exist. Its grip at large scales forms the cosmic web that stretches across space, like an intricate tapestry of light. Gravity is the reason the universe has a story. Without it, there would be no stages of evolution, no cycles of formation and destruction, no architectures of complexity. Every event that unfolds on a cosmic scale carries the imprint of gravity. To appreciate what it means to reverse entropy or reverse gravity, we must begin by recognizing how deeply the universe depends on the alignment of these two arrows. The next movements of thought will push us toward the edges of what physics allows and what physics forbids. Before that leap, the narrative must complete its foundation. One arrow is entropy, the other is gravity. Together, they direct the flow of cosmic history. With gravity now introduced, we are ready to explore what it would mean to challenge these arrows in turn. Gravity continues shaping the universe long after the first stars ignite. Once a star begins burning, gravity works in quiet partnership with nuclear reactions to determine the star's lifetime, its luminosity, and the manner of its death. Inside the core, particles collide with such ferocity that they fuse into new elements, each reaction creating outward pressure that pushes against the inward pull of gravity. This fragile balance defines the star's entire existence. When the outward pressure weakens, gravity tightens its grip. When the core contracts, heat rises, new reactions begin, and the star adjusts its structure. It breathes through cycles of equilibrium shaped entirely by the dance between compression and radiation. This same balance governs planets as well. A newborn planet forms when dust grains drift gently within a disk and collide softly enough to stick together. Over time, the growing body sweeps up more material, becoming massive enough for gravity to round it into a sphere. Molten interiors, oceans, atmospheres, and weather systems all appear through processes ultimately driven by gravity compressing matter and releasing energy. Even the stability of a planet's orbit is a gravitational negotiation between the star's pull and the planet's motion through space. Without gravity, the idea of a world would be meaningless. The cosmos would hold no place stable, enough for complexity to arise. Consider the structure of the galaxy that surrounds us. Our own galaxy contains hundreds of billions of stars, bound by a collective gravitational field that extends far into the dark regions of space. Within this vast system, stars orbit the center in elegant paths that take hundreds of millions of years to complete. Gas clouds drift through these orbits, compressed in some regions and stretched in others by gravitational influences. These cyclical compressions can trigger bursts of star formation, so the very shape of a galaxy contributes to the birth of future generations of stars. Gravity thus becomes a kind of cosmic memory. It preserves motion over immense timescales, passing patterns of density and rotation from one era of the galaxy to the next. The most dramatic gravitational engines of the cosmos reside in the centers of galaxies, where supermassive black holes anchor the surrounding stellar systems. These black holes form not from a single collapsing star, but from repeated mergers, accretion events, and collective gravitational evolution. Their masses can reach millions or even billions of times the mass of a star, yet all of that mass is contained within a horizon so small that nothing inside can communicate with the outer universe. Near these immense objects, space curves so intensely that matter spirals inward in luminous disks that shine brighter than entire galaxies. The heat released in this fall is a direct consequence of gravity converting the potential energy of matter into radiation and then into entropy. This conversion is not incidental. It is one of the major drivers of thermodynamic evolution on cosmic scales. Even the quiet dark matter that permeates the universe obeys gravity's influence. Though invisible, dark matter provides the gravitational backbone for galaxies and clusters. It gathers into halos that shape the distribution of normal matter. Without dark matter, the universe would never have developed the large-scale structures we observe. Stars and gas alone would not have clumped quickly enough. Dark matter amplifies gravitational effects, allowing the cosmic web to emerge. That web forms the lattice on which galaxies align, stretching across space in intricate filaments separated by colossal voids. These patterns reflect the earliest fluctuations in the young universe, but are refined through countless gravitational interactions. Once again, gravity acts as the sculptor, turning small asymmetries into grand architecture. This architecture reveals something subtle about gravity. It organizes the universe not by imposing order, but by guiding matter towards states that release energy and increase entropy. When a galaxy forms, the gravitational collapse warms gas, ignites stars, and floods the surrounding space with radiation. When galaxies collide, the chaos that follows produces shockwaves, starbursts, and streams of debris. Each event increases entropy. Gravity, therefore, accelerates the universe toward complexity while simultaneously driving the overall rise of disorder. These two directions seem opposed only at first glance. In truth, they are threads of the same cosmic process. This leads to a profound insight. Gravity does not simply shape matter, it shapes the possible histories of the universe. It determines which paths are stable and which dissolve. It limits the ways energy can be arranged and provides channels through which new complexity emerges. Without gravity, the universe would be a diffuse smear of particles spreading endlessly apart. There would be no stars to illuminate space, no planets to harbor life, no cycles of birth and destruction to enrich matter with heavy elements. There would be no story. The cosmos would be silent and uneventful. The arrow of gravity is therefore as important as the arrow of entropy. Both arrows point toward a universe unfolding from relative simplicity into vast diversity, driven by forces that increase entropy while building structure. This duality is not an accident. It is written into the laws of physics at every scale. Yet this alignment is also delicate. Change either arrow and the universe would evolve in a radically different direction. The growth of structure would cease. Time itself would lose its coherence. The equilibrium that allows stars to shine and planets to remain stable would vanish. If we imagine a universe where gravity operated in reverse, where it pushed instead of pulled, every scene described so far would collapse into impossibility. No collapse of gas clouds, no ignition of stars, no orbiting planets, no spiral arms, no black holes anchoring galaxies. A repulsive gravitational force would erase the foundational patterns that shape the cosmos. But before speculating on that inversion, we must continue exploring gravity's full natural form. Only then can we appreciate the magnitude of what reversing it would truly mean. The next part of this chapter will deepen the investigation, showing how gravitational evolution becomes irreversible on cosmic scales and how this irreversibility forms the second great arrow of the universe. Gravity reveals its irreversible character most clearly when we look at processes that cannot be undone by any natural means. A collapsing star cannot re-expand into its earlier form because the very act of collapse releases energy that escapes into space. That lost energy cannot be recollected and returned to the star with perfect precision. Once the radiation has spread outward, once the heat has dissolved into the larger cosmic sea, the original state cannot be rebuilt. This irreversibility is not a failure of the laws of physics, but a reflection of probability. There are countless ways for the collapse to proceed. and only a vanishingly small number of ways for the entire process to run backward. Gravity uses this imbalance to carve direction into cosmic evolution. Imagine two galaxies drifting toward one another over billions of years. Their mutual attraction pulls them closer. Their outer stars stretch into tidal streams. Gas clouds collide and heat up. Shock waves ripple through the interstellar medium. New stars ignite in brilliant pockets. Over millions of years, the cores spiral inward, dancing around each other before merging into a larger, reshaped galaxy. These motions could be reversed only if every particle involved knew the exact velocity and position it once held. The heat released during the collision would need to reassemble itself into gas clouds and return quietly to its point of origin. The newborn stars would need to unfuse their atoms and dissolve back into their precursor elements. The probability of such precision is so small that the universe effectively forbids it. Gravity ensures that once events proceed along a certain path, they cannot trace their steps back. This irreversible behavior can be seen even in the gentlest gravitational processes. A comet orbiting a star loses tiny amounts of energy through interactions with dust, solar wind, and radiation. Over many passages, these losses accumulate. The orbit shifts. The comet may eventually collide with a planet or be ejected from the system. This long-term change is permanent. The scattered dust cannot remake the comet. The ejected mass cannot return itself to its original state. Gravity creates motions that drift into new configurations and leave the past behind, adding yet another layer to the arrow of time. Black holes stand as the ultimate expression of gravitational irreversibility. When matter crosses an event horizon, it cannot return. The information it carries becomes encoded in the horizon's area, but this encoding is so deeply scrambled that no known process could reconstruct the original state. Even as black holes slowly evaporate through quantum processes over unimaginable spans of time, the emitted particles carry only faint traces of the complexity that once fell inside. The simplicity of the radiation contrasts with the richness of the matter that entered. This contrast marks a one-way loss of accessible information. Gravity therefore becomes a guardian of entropy growth, ensuring that some events cannot be undone, even in principle. This cosmic irreversibility extends to the scale of galaxies and clusters. As structures grow under gravitational influence, they merge, collide, and settle into shapes defined by collective motion. A group of galaxies interacting over billions of years will settle into a form that reflects the energy they have radiated into the background. Reversing such an interaction would require gathering that radiation, reconcentrating it, and guiding it along precisely the right paths to retrace the full history of the cluster. Again, the probability is beyond negligible. Gravity constructs pages in the cosmic story that cannot be erased or rewritten. Once written, they guide what comes next and constrain what can ever occur again. Every irreversible gravitational process intertwines with the rise of entropy. When a star forms, heat escapes into space and entropy rises. When galaxies merge, shock waves dissipate energy and entropy rises. Even the gentle settling of planets into stable orbits reflects dissipative processes that increase entropy. This mutual reinforcement gives the universe a coordinated direction. While entropy pushes systems toward greater multiplicity of microstates, gravity pushes matter toward deeper wells of potential energy, where that multiplicity can grow even faster. Both arrows point the same way across cosmic time. They shape the universe together, each amplifying the influence of the other. The deepest insight here is that gravity is not simply a force that pulls. It is a force that shapes the possible histories of matter. It prunes the tree of possibilities. It allows some paths and forbids others. Once matter has fallen into a new configuration, the likelihood of returning to an earlier state becomes essentially zero. This is why the large-scale structure of the cosmos appears as it does. Filaments thread the universe, clusters gather at their intersections, and voids stretch between them. These features reflect gravitational evolution that cannot be undone. They are the cosmic equivalent of footprints in sand that can never be smoothed again. If gravity were somehow reversed, this entire architecture would not merely behave differently, it would unravel. A repulsive gravitational force would destroy the stability of orbits. Stars would expand and dissipate. Galaxies would fly apart. Black holes would not form, or if they already existed before the inversion, they would discharge their contents in ways beyond current understanding. Yet even such an extreme idea cannot be approached until the full natural arrow of gravity is understood. With this part complete, the narrative is ready to move into the strange conceptual terrain of reversing fundamental laws. The next chapter will ask what it means for physics to operate in reverse, and how the equations of motion, which allow symmetry in principle, give rise to arrows of time and structure in practice. Only by confronting these subtleties can we imagine a universe where gravity repels and entropy falls, and only then can we grasp the unimaginable consequences of turning the cosmic arrows around. To speak of reversing a fundamental law is to walk into territory where intuition falters. At first glance, it seems simple. One might imagine pressing a cosmic rewind button and watching every event unfold backward. But the laws of physics do not include such buttons. They describe how systems evolve through equations that are symmetrical in time. If you take the motion of a particle, replace time with its negative, and run the equation again, the motion is still a valid solution. This symmetry is woven into quantum mechanics, classical mechanics, and the geometry of space that underlies gravity. Nothing in the equations prefers forward over backward. To them, direction is irrelevant. Yet to us, direction is everything. The challenge lies in understanding how these time-symmetric laws produce a universe where processes unfold in only one direction. A glass shatters, but does not reassemble. Heat flows from hot to cold, and never transitions in the opposite sense. Stars burn their fuel and do not refill it. These asymmetries emerge not because the laws forbid their opposites, but because the conditions required to run the film backward are so specific that the universe will never encounter them naturally. The equations permit them, reality does not. This reveals a subtle truth. When we talk about reversing entropy or reversing gravity, we are not imagining laws being rewritten. We are imagining boundary conditions changing. The laws would still hold, but the universe would be placed in an arrangement where the usual direction of evolution becomes inverted. This distinction matters because it highlights how deeply the arrows of the universe depend on initial conditions rather than mathematical structure. If the cosmos had begun in a high entropy state rather than a low entropy one, time might not have a recognizable direction at all. Every moment would look as random as any other. Events would not form sequences with meaningful order. The very idea of history would dissolve. Understanding this allows us to see why reversing entropy is equivalent to demanding an extraordinarily unlikely configuration of microscopic details. To reverse the arrow of entropy, you must begin in a state where there are far fewer microstates available in the future than in the past. This means the future becomes narrow and ordered, while the past becomes broad and chaotic. Such a universe would not flow from simple beginnings into complex structures. It would flow from complexity into simplicity. Clouds would gather themselves from random gas. Stars would unfuse their elements. Broken stones would restore their shapes. Fallen trees would rise and rejoin their branches. Every process would rewrite its own outcome in reverse. But these fanciful images miss something deeper. Reversing entropy is not the same as playing events backward. It is not a mirror of the world we know. It is a world with different likelihoods built into its fabric. In our universe, a spilled cup of water spreads into intricate shapes because there are enormously many microstates that correspond to the water being spread out. In a reversed entropy universe, the spread out water would gather itself not because it remembers being structured, but because the structured arrangement would be overwhelmingly more probable. The universe would not be undoing something it had done. it would be moving toward its natural state, given its reversed boundary conditions. To imagine this correctly, picture not the past coming back to life, but the future collapsing into tighter and tighter patterns as time moves forward. Rather than states differentiating and scattering, they gather into more precise forms. Instead of information being lost, information becomes increasingly clear. The arrow of time flips. Causes emerge from effects rather than effects emerging from causes. Precision grows instead of dissipating. The physics is consistent, but the narrative of events becomes unfamiliar. Reversing gravity requires a different kind of conceptual shift. Gravity arises from the curvature of space caused by mass. Objects move in the straightest available paths through this geometry. If we imagine reversing gravity, we are not simply flipping a sign in an equation. We are altering the way space bends. Instead of curving inward around mass, space would curve outward. The straightest paths would diverge instead of converge. Two objects placed near each other would drift apart without hesitation. Structures would not form. Collapses would not occur. The cosmos would not sculpt itself into stars and galaxies. Yet gravity is more than a geometric influence. It also acts as a channel for energy to dissipate. When matter collapses, gravitational binding energy is released, which increases entropy. If gravity were reversed, collapse would be forbidden. This means many processes that currently produce entropy would no longer operate. The thermodynamic behavior of the universe would be rewritten. The very mechanisms that allow entropy to rise efficiently would vanish, and the story of cosmic evolution would lose its familiar shape. When both entropy and gravity act in their usual directions, the universe evolves into structures that shine, merge, collapse, and disperse. This is the natural flow given the initial conditions. But if we reverse one arrow or the other, the rules of likelihood change, and with them, the fabric of cosmic history. A universe where entropy decreases or gravity repels is not simply the same universe with the film reversed. It is a different landscape of possibilities, governed by the same equations, but driven by unusual boundary conditions. To understand how extreme these inversions truly are, we must now focus on the first of the two arrows. What would it mean for entropy to run backward? What phenomena would arise? How would stars behave? How would life behave? And what would an observer inside such a universe experience? Only by confronting these questions can we begin to appreciate the magnitude of reversing the direction in which probabilities flow. Reversing entropy requires far more than imagining broken objects knitting themselves back together or smoke returning to a candle. Those pictures rely on a human sense of what a reversed event should look like, but the true physics is stranger. In our universe, entropy increases because there are overwhelmingly many more ways for systems to be spread out, mixed, irregular, or thermalized than for them to be arranged in precise and delicate patterns. When you pour cream into coffee, you witness this principle directly. The swirling patterns blend into one another until no trace of the original separation remains. This happens not because the laws of physics force the mixture to become uniform, but because the number of microscopic arrangements associated with a uniform mixture dwarfs the number associated with separation. The system naturally drifts into the region of greatest statistical weight. In a universe where entropy decreases, this logic inverts. The uniform mixture would not be the most probable state. Instead, the future would be dominated by precise and highly structured patterns. The cream would gather itself not because it remembers the past, but because the reversed boundary conditions make the separated state overwhelmingly more probable. The swirls would assemble into ordered shapes, tightening with every moment as the system climbs toward a low entropy configuration. If you watched this process with expectations shaped by our universe, you would think time were running backward. But in that reversed world, it would be running forward. The difference is not in the laws, but in the statistical environment in which they operate. heat transport would behave in a way that appears impossible from our perspective. A cold object would spontaneously warm as heat flowed into it from its cooler surroundings. Not because energy breaks its rules, but because what we call the less likely path becomes the overwhelmingly likely one under reversed entropy. Every tiny fluctuation that occasionally, in our world, causes a microscopic amount of heat to move from cold to hot would be magnified and supported by the reversed statistical landscape. These improbable fluctuations would chain together into a dominant trend. The result would be a universe where every thermal process moves opposite to what we consider natural. Life in such a world would face conditions unlike anything familiar. Biological organisms rely on the forward flow of entropy to fuel metabolism, growth, and memory formation. Cells depend on gradients that dissipate. Proteins fold by releasing energy into their surroundings. Neural networks form memories by creating patterns that raise entropy in the brain and its environment. If entropy decreases instead, every step of life's functioning becomes inverted. Energy would not dissipate in expected ways. Chemical reactions would tend towards states of lower disorder. Structures would appear not because they consume free energy, but because the future demands them. Memory would not encode past events. It would assemble itself from future constraints. A person would not grow older in any conventional sense, for aging is a product of entropy increasing within biological systems. Instead, one might grow sharper and more ordered with time, reversing the entire logic of metabolism. These consequences do not imply that such a universe is impossible in the mathematical sense. The equations governing microscopic motion do not forbid entropy from decreasing. They simply do not support it under the boundary conditions of our cosmos. If those conditions were replaced by others that favor low entropy futures, a decreasing entropy universe could exist, but it would be incomprehensible to any observer shaped by the physics we know. Events would appear coordinated with impossible precision. A dropped object might rise into the hand before the hand reaches for it. A cloud of gas might gather itself into a star without any collapse, as though the universe were assembling ingredients rather than dispersing them. The entire flow of time would carry a tone of inevitability, not toward increasing disorder, but toward decreasing complexity. This inversion of entropy has profound implications for the arrow of cause and effect. In our universe, causes precede effects because information becomes increasingly scrambled as time progresses. Events lose detail. Their influences spread outward, creating a widening cone of possibilities. In a decreasing entropy universe, the cone narrows instead. Effects determine causes. Observers would see outcomes converge into more specific states. The future would not be open, it would be constrained. A person would not experience uncertainty about what tomorrow might hold. The future would be the anchor. The past would be the direction of freedom. To understand how profoundly this changes the flow of time, consider the behavior of quantum systems. In our world, quantum processes follow probabilistic rules, and measurements collapse a wave function into one of many possible outcomes. The collapse is not time reversible. It increases entropy by selecting a specific result from a range of possibilities. In a reversed entropy universe, measurement would work in an opposite manner. A measurement would not collapse possibilities into one outcome. It would refine possibilities. Instead of losing information, the observer would gain it. Observations would narrow the set of past events rather than determine future ones. Every act of measuring would be an act of reconstructing what had already been constrained by the low entropy future the universe is moving toward. This reorientation reveals how delicate our sense of time truly is. Time feels like an absolute, yet its direction emerges from a statistical imbalance between the number of accessible states in the past and the number accessible in the future. Reverse that imbalance and every physical intuition we hold fails. We do not simply witness events in reverse. we inhabit a world whose internal logic is reversed. Chemistry, biology, and cosmology rearrange themselves around this new statistical landscape. Nothing looks the same, not because the laws have changed, but because what is overwhelmingly probable has changed. Reversing entropy is therefore an idea that sits somewhere between possibility and impossibility. The laws permit it, the universe does not. It is a mathematically valid realm that reality never visits because the boundary conditions of our cosmos anchor time in the direction of increasing disorder. To cross into a reversed entropy world, we would need to change the initial state of the universe itself. We would need a cosmos that began in a high entropy state and evolves into a low entropy one. Such a cosmos would not merely run backward. It would have no resemblance to ours, except in the symmetry of its equations. With this understanding of entropy's reversibility, the next step is to consider gravity's behavior under similar inversion. Gravity is not just a force that pulls, it is a geometric consequence of mass shaping the structure of space. To reverse gravity is to bend the geometry of the universe outward instead of inward. What would this do to stars, planets, and the grand cosmic structures that fill the night sky? How would matter behave if every mass repelled instead of attracted? The consequences reach far deeper than simply pushing objects apart. Reversing gravity is not a matter of flipping a sign in an equation. It is a reshaping of the stage on which all motion unfolds. Gravity is the curvature of space created by mass. Objects move along the straightest possible paths available within that curvature. When gravity pulls, it is because space bends inward around matter. When two objects draw closer together, they are not being pulled in a literal sense. They are following straight paths through a geometry that narrows between them. To reverse gravity, space must bend outward instead. The straightest paths must diverge. Objects must drift away from one another, not because a new force pushes them, but because the fabric of space guides them apart. This outward curvature would touch every scale of structure. The star that forms from a collapsing cloud would never ignite. The cloud would not collapse in the first place. Instead, it would slowly expand, thinning until its density becomes so low that no meaningful structure could arise. The elaborate choreography of dust turning into planets would disappear. Without inward curvature, orbits cannot exist. A planet travels in a curve only because space converges around the star. If space diverges, the planet flees. What we call a stable world would be an impossibility. No oceans, no continents, no atmospheres, no living beings tracing their origins through time. The very concept of a galaxy would dissolve. A galaxy forms because small density variations grow under gravitational attraction. Gas gathers, stars ignite, clusters grow. But with repulsive gravity, density fluctuations would smooth out instead. Any slight concentration of matter would be erased as space pushes outward around it. The delicate spirals, the bright cores, the grand arcs of starlight stretching across millions of trillions of kilometers would never appear. The cosmos would resemble a canvas constantly flattening itself, erasing every attempt at structure. Black holes, the most extreme expressions of gravitational collapse, would be forbidden. The inward curvature required to trap light would not exist. If gravity were reversed after black holes had already formed in a previous era, these objects would not remain stable. The horizon would lose its defining feature as the surrounding geometry shifted from converging inward to diverging outward. Matter and information long trapped could surge outward in unfamiliar ways. The encoded entropy within the horizon, which in our universe is vast beyond imagination, would become exposed. The release of this information could transform the surrounding regions, emptying the depths of complexity that gravity once concealed. Repulsive gravity would not simply erase structure, it would erase the paths by which complexity emerges. In our universe, gravitational collapse releases energy that increases entropy and fuels processes that lead to richer patterns of matter. In a reversed gravity universe, there is no collapse, no ignition of stars, no sustained energy sources. Entropy would not rise in familiar ways. Instead, it would drift toward uniformity with extraordinary speed. The universe would become empty, smooth, and quiet, not through the slow march of heat death, but through the immediate absence of any mechanism that could create gradients or sustain the flows necessary for complexity. This reveals something essential about the arrow of gravity. It is not merely a tendency for matter to clump. It is a pathway for the universe to explore deeper layers of structure, releasing energy along the way. It allows the cosmos to build mountains of information, to weave patterns that stretch across space, to form engines of light that shine for billions of years. Gravity shapes history. It creates chapters. It gives rise to eras of formation and destruction. Without it, time loses texture. Events lose scale. A repulsive gravitational world is not a universe with different scenery. It is a universe without story. When we imagine reversing gravity, we are imagining a universe where every structural pattern becomes unstable. Every star dismantles itself. Every planet unbinds. Every galaxy dissolves. Even atomic structures would drift into instability because the slight gravitational contributions that play a role in cosmic equilibrium would be replaced by outward pushing curvature. Chemistry may still function on the smallest scales, but it would lose the cosmic environment that allows it to flourish. Molecules could exist, but worlds could not. Life as we understand it could not originate, because life requires gradients, stability, and sustained energy flows. Repulsive gravity would erase each of these conditions before they could begin. Yet reversing gravity alone does not present the full picture. The arrow of gravity works in concert with the arrow of entropy. Together, they define the evolution of the universe. If gravity is reversed, but entropy continues to increase, the universe would unravel into a cold and structureless expanse. If entropy is reversed, but gravity continues to attract, the universe would attempt to create ordered futures within a framework that drives matter inward. The tension would produce outcomes stranger than either arrow reversed alone. And if both arrows are reversed at once, the universe would not simply run backward. It would unmake itself. To understand such possibilities, we must now leave the realm of inversion as a conceptual symbol and step into the thought experiment fully. What does a universe look like when entropy runs backward? What does it look like when gravity pushes outward? And most importantly, what does it mean for observers within such a universe whose own cognition depends on the arrows we take for granted? Entropy is the quiet architect of time's direction, and when it rises, the universe flows into wider and wider realms of possibility. If entropy were to fall instead, the flow would reverse, pulling events toward ever narrower states. To imagine the world under such a rule is not to imagine everything simply running backward like a reversed recording. A reversed entropy universe is not the same story played in reverse order. It is a different story governed by different probabilities, driven by different expectations, shaped by a future that is more constrained than its past. When entropy falls, the universe does not undo what it previously did. It becomes something that naturally moves into increasing clarity and precision, just as our universe naturally moves into greater dispersion and disorder. Consider a familiar scene. A cup of warm tea cooling on a table. In our universe, heat flows from the warmer tea to the cooler air because there are far more microstates associated with the heat being spread out than with the heat remaining concentrated. If entropy ran backward, the more probable direction would be the opposite. Heat would flow into the tea, not because some hidden force commanded it, but because the future low entropy state requires that concentration. Every microscopic fluctuation that rarely moves energy from cold to hot in our world would become amplified and aligned, producing a natural flow from cooler regions into warmer ones. The cooling process would not simply reverse. the laws would make heating the natural outcome of time advancing. This inversion carries profound implications for stars. A star burns because fusion moves from simple states to more complex ones, releasing energy and raising the entropy of the surrounding universe. In a decreasing entropy world, these reactions would lose their statistical favor. The pathways that increase entropy would become the rarest ones, while the pathways that decrease entropy would dominate. Instead of hydrogen fusing into helium, the high-entropy ashes of nuclear reactions would statistically tend toward their simpler precursors. A star would unburn. Its core would gently transition back toward lower mass elements. Radiation previously emitted into space would converge inward. What appears impossible in our universe would become inevitable in that other cosmos. A star would gather light rather than cast it, restoring its fuel rather than consuming it. Planets would also follow this strange rule. Geological processes that raise entropy by dispersing heat and cracking structures would instead tend toward restoration. Eroded landscapes would sharpen. Mountains worn by winds would rise in growing precision. The interior of a planet, which in our universe cools gradually over billions of years, would warm from surrounding materials realigning into ordered states. Volcanoes would not erupt randomly. They would appear to reclaim previously distributed minerals, concentrating them once, again. Everything would drift toward refinement, not fragmentation. It would seem as if the world were healing itself, but in truth, it would be following the natural pull of its reversed thermodynamic future. Life introduces even more dramatic consequences. Living organisms rely on the increase of entropy to function. They import energy, release heat, generate chemical disorder, and use these processes to sustain metabolism and growth. Memory, in particular, is inseparable from the rise of entropy. Neurons form stable patterns by changing physical structures within the brain. These changes require energy and raise entropy internally. In a universe where entropy falls, memory would form backward. An observer would not remember past events, but would recall the future. The future would guide cognition. A person would experience life as a gradual sharpening of identity rather than a diffuse aging. Knowledge would increase, not because of gathered experience, but because the low entropy future demands that knowledge exists. Every recollection would feel like a revelation of what is coming, rather than what has been. This reshaping of memory alters the logic of causality itself. In our world, causes precede effects because the spread of information and energy limits what effects can occur. With entropy decreasing, causes would be constrained by effects. You would move because you are already in the state that the future requires you to inhabit. The free unfolding of possibilities would narrow into a single path. Uncertainty would fade as the universe relentlessly approaches its low entropy destination. The freedom associated with open futures would disappear. What we call the future would feel fixed, while the past would feel open and unresolved. Microscopic processes would mirror this grand rearrangement. In our universe, the collision of molecules spreads energy irregularly, creating thermalization. In a reversed entropy universe, the collisions would gradually align instead of randomize. Molecules would move with increasing coordination. Gas clouds would refine their motions rather than scatter. Turbulence would fade naturally, not through friction, but through the statistical dominance of ordered microstates. The dance of particles would appear choreographed, as though guided by an intelligence. But the guidance would be purely statistical. The future dictates order, and the matter drifts into it. The formation of celestial bodies would also shift in counterintuitive ways. In our universe, dust clouds collapse into stars because the collapse raises entropy in the surrounding space. In a decreasing entropy world, the collapse would not occur. Instead, the dust would concentrate in increasingly particularized patterns without releasing heat. Stellar birth would not be an ignition, but an absorption. Light that once escaped would be drawn back in. the surrounding space would lose freedom as photons settle into narrower distributions. If such a universe contains black holes, their behavior would be radically altered. Black holes carry enormous entropy in our universe. They are the most entropic objects known. A decrease in entropy would require black holes to evaporate, not through the slow quantum process described in theoretical work, but through sudden release of stored information. Instead of absorbing matter and hiding complexity behind horizons, they would disgorge complexity, emitting structured radiation as they unwind. The information that once disappeared into the depths of a black hole would become visible again. Observers would witness the unspooling of cosmic history encoded within the hole, light emerging in patterns of clarity rather than thermal randomness. The greatest shift would appear at cosmic scales. In our universe, the expansion of space spreads galaxies apart and raises entropy by increasing the number of available arrangements matter can take. In a reversed entropy universe, the expansion would not create diversity, it would create convergence. Structures would move into refined configurations. The cosmic microwave background, instead of growing fainter, would gain definition over time, gathering itself into a more specific pattern. The entire universe would reshape itself toward a highly ordered final state. If we walked through such a universe, we would not feel chaos reversing. We would feel inevitability growing. Every object, every event, every breath would be pulled toward order with the same certainty with which our world moves toward disorder. Entropy running backward is not simply a reversal. It is a cosmic script written in narrowing lines. Now that the arrow of entropy has been inverted in concept, we can turn to the other arrow, the one that governs structure. For even if entropy pulls the universe toward order, gravity shapes the pathways matter can take as it moves. Gravity has its own direction, its own irreversibility, and its own role in the unfolding of cosmic history. To reverse it is to rewrite the landscape of motion itself. But before that combined inversion can be explored, we must see what happens when gravity alone loses its familiar pull and becomes a force that pushes. If gravity were to change its sign, the universe would feel the change instantly. There would be no gentle transition, no slow adjustment as structures negotiated new forces. Attraction would become repulsion, and the geometry of space that once curved inward around mass would bend outward instead. Every object would drift not toward others, but away from them. This shift is not a matter of force alone. It is a transformation in the shape of reality, because gravity is not a pull in the ordinary sense. It is the way mass shapes the paths that objects consider straight. When those paths diverge instead of converge, the universe loses its ability to gather matter into stars, planets, galaxies, or any of the structures that give cosmic history depth and character. The first victims of repulsive gravity would be the stars. A star exists only because gravity compresses matter densely enough for fusion to ignite. If gravity begins to push outward, the core can no longer sustain its pressure. The balance between inward compression and outward radiation collapses. The star does not explode. Explosions require confinement. Instead, the star swells and thins. Its layers drift outward, turning from a bright sphere into an expanding haze. Light that once streamed from the surface slows and folds back as the geometry reshapes around the dissolving mass. The star becomes a cooling cloud, its nuclear history erased as material spreads into a uniform mist. Planets would fare no better. A planet is a victory of gravity over fragmentation, a soul of dust that gathered itself into a sphere by persistent compression. Without that compression, the sphere would unbind. The crust would fracture, the mantle would rise, and the core would weaken. The planet would puff outward like a soft bubble losing cohesion. Oceans would spread into space as thin vapor. Mountains would drift into dust. Atmospheres would vanish into expanding shells. The very concept of a world would become impossible because nothing would remain stable enough to support shape or boundary. The collapse of planetary systems would be followed by the unraveling of galaxies. In the universe we know, Galaxies form from regions of enhanced density that grow under mutual attraction. Stars orbit within them because they follow straight paths in a space curved inward by the combined mass. With repulsive gravity, this curvature bends outward instead. Every orbit becomes unstable. Stars drift away from the center. The graceful spirals that once spanned millions of trillions of kilometers dissolve as easily as fog in sunlight. The central bulge loses coherence. The galactic disk fractures into streams. Regions that held their pattern for billions of years become unbound in mere moments of cosmic time. The galaxy does not collapse. It evaporates. Clusters and superclusters of galaxies, which depend on the faint but persistent pull of gravity across immense distances, dissolve even faster. Their filaments stretch and thin. Their intersections empty themselves. The cosmic web unravels into separate strands, then into scattered fragments, then into near uniformity. Repulsive gravity wipes away the memory of every gravitational structure ever formed. The universe becomes smooth not through slow erosion, but through sudden divergence, as though all mass were retreating from every other mass with equal determination. Black holes stand as the most dramatic centers of gravitational collapse, so repulsive gravity affects them in extraordinary ways. A black hole exists because no known pressure can overcome the inward curvature of space at its boundary. If this curvature flips, the horizon cannot survive. The region where light once could not escape becomes a region where light cannot remain. Information that fell into the black hole over its entire lifetime would rush outward. The event horizon would unwind. The interior would not re-expand into its earlier form, because the collapse erased any recognizable structure, but the stored information would be released in patterns far more complex than simple radiation. It would not be a violent explosion. It would be a steady discharge of the deepest content the universe has ever hidden. If this release occurs everywhere at once, the universe would become flooded with signals carrying the memories of long-vanished stars, planets, and civilizations. It would not be a replay of their histories, but an outpouring of their informational signatures. This moment would be the closest thing a repulsive gravity universe could have to cosmic illumination. Yet it would be illumination without structure, an unfocused glow of lost complexity, spreading into a geometry that can no longer hold shape. Repulsive gravity would alter even the smallest scales of matter. Although gravity is enormously weaker than the electromagnetic force that holds atoms together, it still plays a role in the overall environment that allows chemistry to flourish. Atoms form clouds, clouds gather into molecules, molecules assemble into solids or liquids, and these structures require stable surroundings. If everything is expanding away from everything else under repulsive curvature, molecules experience a constant thinning of density around them. They remain intact, but nothing larger than molecules can remain stable. Crystals cannot grow, liquids cannot pool, biological systems cannot emerge. Life requires gradients, confinements, and sustained flows of energy, none of which can exist when space encourages matter to diverge. In such a universe, energy behaves differently as well. Inward curvature allows energy to concentrate. Stars ignite because mass gathers. Accretion disks glow because particles spiral inward. Supernovae occur because collapse reaches critical thresholds. With repulsive curvature, none of these mechanisms exist. Energy cannot concentrate. There is no ignition, no collapse, no compression. Photons scatter endlessly. Heat never builds into anything. The universe becomes a vast stage without props, actors, or events. It is a place where nothing can keep hold of anything else. The cosmic expansion accelerates dramatically under repulsive gravity. Even in our universe, a form of repulsive influence exists through dark energy, yet its reach is gentle and its effects appear only across immense distances. If gravity itself became repulsive, the acceleration would occur everywhere, at all scales, instant and fierce. Regions that once held together would separate so rapidly that observers would witness the thinning of reality in real time. Distances would inflate, patterns would fade, horizons would broaden faster than any message could cross them. Communication between any two systems would become impossible as space expands faster than signals can bridge it. The universe under repulsive gravity is not chaotic. Chaos requires interactions. This universe is silent. Structures dissolve, and then nothing can reform them. Entropy would rise initially as collapsed systems release energy. But once the divergence settles into uniformity, entropy production would nearly halt. The universe would drift into a smooth and empty state, not because it aged, but because repulsion eliminates the possibility of complexity. It would be a cosmos without stars, without stories, without evolution. To imagine entropy running backward is to imagine reflection sharpening. To imagine gravity repelling is to imagine structure collapsing into smoothness. When these two reversals are combined, the universe becomes a landscape where neither time nor form behaves in recognizable ways. The next chapter moves into this combined world, where both arrows fail and reality reshapes itself into a cosmos that does not reverse the familiar story, but creates an entirely different one. To imagine a universe running backward is not to imagine a simple reversal of scenes, as though all of cosmic history were a recording being played in reverse. True reversal, the reversal of both gravitational and entropic arrows, transforms the very grammar of existence. It replaces the familiar logic of evolution with an alien logic of convergence. Instead of events growing outward from simple origins into sprawling complexity, they shrink inward toward a final state of extraordinary precision. Instead of structures forming through collapse and accumulation, they dissolve while drifting into patterns that seem etched by a guiding intelligence. This universe is not our universe undone. It is a universe that has always moved toward a future more ordered than its past, shaped not by the widening of probability, but by the narrowing of possibility. In the earliest era of such a cosmos, everything would appear chaotic to an observer from our world. Yet this chaos would be an illusion born from unfamiliar expectations. What we call chaos would in that universe be the broadest region of possibility, consistent with the low entropy future that lies ahead. The beginning would contain vast diversity because that diversity allows for the greatest number of narrowing pathways to converge into the sharply defined end state. Unlike our universe, which unfolds from an exquisitely low entropy beginning into higher entropy futures, this reversed cosmos begins in what appears to be maximal richness. It is a frontier full of branching paths, but each branch is destined to merge into others, like rivers flowing toward a single delta. Matter in such a universe never collapses into stars, for repulsive gravity forbids collapse. Instead, vast gas clouds drift into delicate structures. These structures become more refined with time, not through compression, but through careful reorganization as entropy decreases. The gas does not fragment into star-forming clumps. It separates into smoother sheets and filaments, as though invisible hands were smoothing creases from a cosmic fabric. As entropy falls, the microstates available to the universe shrink. Each moment eliminates possibilities rather than creates them. The cosmic canvas becomes sharper, more definite, less open to variation. Radiation behaves in a way far more dramatic than matter. In our universe, light spreads outward, scattering, thermalizing, diluting its information. In a backward-running universe, light does not scatter. It concentrates. A photon that might in our world disperse into an ocean of randomness instead aligns with other photons, joining in narrower and more precise wave patterns. The cosmic background radiation would not fade into uniformity over billions of years. Instead, it would gain detail. Faint irregularities would sharpen into fine structures of remarkable clarity. These structures would not map the early universe. They would map the universe's destined end. Observers would watch the sky grow more defined with time, as though the night were quietly revealing a hidden message inscribed into the future. Black holes offer the clearest window into this inverted cosmos. In our universe, they represent the highest entropy objects known, vast repositories of hidden information and thermodynamic weight. In a universe where entropy must fall, that weight cannot remain locked behind horizons. A black hole could not persist in this reversed physics. Its existence would be a violation of the universe's required direction. Instead of swallowing information, it would disgorge it. Not in violent bursts, but in long streams of sharply structured radiation. Each stream would reflect the information that had once fallen inside. The horizon would shrink with unnerving elegance, not through a slow quantum evaporation, but through an orchestrated unraveling. The release would be a kind of cosmic remembering, the universe recovering details it had once concealed. As black holes dissolve, they seed the cosmos with structured patterns that move it toward its low entropy future. These patterns would influence everything around them. Clouds of gas would shift in response to the subtle rearrangements of radiation. Electrons and protons would settle into constrained patterns, as though guided by a music that grows more distinct with each passing moment. Space would fill with signals rather than noise, and these signals would increasingly dictate the behavior of matter. In place of the chaos of gravitational collapse, there would be a grand choreography of divergence and refinement. Galaxies would be among the first large-scale structures to vanish under repulsive gravity, but they would not disappear abruptly. They would stretch, drift, and thin until the once luminous spirals become faint arcs, and then wisps, and then imperceptible lines of matter. As they thin, the entropy decreases, for the thinning is not random dispersal, but a movement towards specific configurations. The dissolution of galaxies would seem almost graceful, like ink spreading on water before settling into a perfect stillness. The cosmos would lose its grand architecture of stars and clusters, but it would replace that architecture with something subtler, a universe whose large-scale structure becomes extremely smooth while its microscopic and radiative structures become increasingly refined. Time in this universe would feel profoundly different. Observers would not feel themselves drifting from ordered beginnings into scattered futures. They would feel themselves tightening into a framework that allows fewer and fewer variations. Their own thoughts would feel drawn toward a future that dictates their patterns of reasoning and memory. Memories would accumulate, not from experience, but from the narrowing of possible histories. People would remember tomorrow more clearly than yesterday, because tomorrow's low entropy destiny is the anchor toward which their cognition flows. The past would feel loose, changeable, uncertain. The future would feel rigid, fixed, inevitable. In such a universe, cause and effect would not vanish, but would invert. Events would be interpreted through the lens of their outcomes. A particle that behaves oddly would not be seen as deviating from a rule, but as fulfilling the requirement of the final state. Scientists in such a cosmos would not ask what past events led to the present, but what future constraints shaped the present. Predictions would not be extrapolations forward, but reconstructions backward. The logic of science would remain intact, but its orientation would be flipped entirely. Energy behaves differently as well. In our universe, energy flows from high concentration to low concentration, driving heat engines, weather patterns, and biological processes. In this reversed universe, energy flows inward, not outward. Heat moves toward concentration, narrowing temperature differences. Biological systems, if they could exist at all under repulsive gravity, would not metabolize in ways familiar to us. They would gather energy instead of dispersing it. Their internal structures would refine with time. Aging would reverse not because cells grow younger, but because the thermodynamic conditions make certain molecular patterns more probable as the universe approaches its end. The cosmic expansion accelerates with unrelenting force, driven by repulsive gravity. Regions of matter that begin close move apart exponentially, and yet within those regions, the patterns of radiation and microscopic motion become tighter and sharper. This paradox is central to the reversed universe. Space expands wildly, but information contracts. Matter disperses, but patterns converge. The cosmos becomes emptier on large scales, but fuller on small scales. It is a grand unspooling of structure, coupled with an intense sharpening of detail. Eventually, the narrowing of states reaches its final phase. The universe approaches a condition of nearly perfect order. Motion persists, but every motion is part of a delicate alignment that cannot deviate. Temperature differences are minimal, radiation fields are coherent. Matter is arranged in the most specific configuration allowed by the final boundary. Time continues, but its meaning fades, for nothing new can occur. The universe has reached a state of minimal entropy. It has reached not heat death, but stillness of comprehension, a kind of cosmic final chord where every note aligns into perfect resonance. What would consciousness feel like in such a place? What would a thinking being perceive when its memories are shaped by the future? When its experiences collapse into precise interpretations? When the entire cosmos narrows around it like a funnel, drawing every possibility into one inevitable state? These questions lead naturally into the next exploration, where the physics of reversed arrows meets the inner world of observers. To understand consciousness in a universe where entropy falls and gravity repels, one must first let go of every familiar assumption about how minds work. In our universe, consciousness is inseparable from the forward flow of time. Memory traces form by increasing entropy within neural systems. Learning depends on dissipating energy. Experience accumulates because the future holds far more possibilities than the past. But in a cosmos where these arrows run backward, minds would not be sculpted by the past. They would be sculpted by the future. Their inner landscapes would unfold not from causes seeking effects, but from effects that reach backward through time, shaping the very conditions that permit their existence. Thought itself would become a mirror turned in a new direction. Imagine the formation of a mind in such a world. In our universe, a baby begins with a pliable neural architecture that gradually fills with memories drawn from daily experience. Those memories are encoded through synaptic changes that raise entropy. But if entropy decreases, the process reverses. The brain of a developing being would not grow more complicated by wandering into new microstates. It would become more refined as the future constrains the structure of its neural pathways. Memories would settle into place, not after experiences occur, but as the brain aligns with the narrowing possibilities of the cosmos. A child would not remember early events. The child would remember the future, because the future is the direction of decreasing entropy. The future is the corridor through which the universe is funneling all things. Such a child would experience life as a gradual revelation rather than an accumulation. Thoughts would not arise spontaneously. They would be pulled into existence by the destiny that lies ahead. Every idea that enters the mind would feel certain, as though it were being recalled rather than discovered. Creativity would not be the art of imagining what has never been. It would be the art of perceiving what must eventually occur. The future would cast a long shadow that shapes every neuron, every choice, every dream. These beings would not seek to predict the future. They would treat the future as known and treat the past as uncertain. Because memory formation relies on decreasing entropy, remembering and forgetting would exchange roles. In our universe, forgetting is the natural drift of memory toward disorder, a loss of detail that accompanies neural degradation. In a decreasing entropy universe, forgetting would be the rare and difficult act. It would require the mind to resist the tightening of states. Remembering would be easy because the narrowing future continually clarifies what must be remembered. Forgetting would be like trying to hold a handful of water in our world. The present state of the cosmos would constantly reshape the mind to reflect what is coming, not what has been. Emotion would also take a new form. In our universe, emotions are motions. tied to changing expectations. Joy appears when outcomes surpass what we anticipate. Fear arises when dangers threaten our future. In a backwards-running cosmos, expectation is not directed outward into the unknown, but inward toward the inevitable. Joy would come not from surprise, but from alignment, a feeling of harmony with the narrowing trajectory of the future. Fear would arise when the mind finds itself misaligned, when a thought or action threatens the coherence required by the future state. Such fear would not be fear of death or danger, but fear of divergence, fear of drifting away from the tightening corridor that leads to the final arrangement of the cosmos. Consciousness in such a universe would also experience perception differently. In our world, sensory inputs arrive and the brain interprets them in light of its expectations. But a backward-running universe requires that interpretations be shaped more strongly by what must be seen rather than what is seen. Vision would not simply gather photons, it would refine them. The observer would perceive the world in a way that reinforces the narrow possibilities the future demands. Light itself aligns under decreasing entropy, so perception would become sharper with time. Observers might witness a world that grows more crystalline, more defined, more structured, as entropy falls. Nothing would blur with age. The world would intensify. Language and communication would adapt to this logic. In our universe, language evolves because new experiences require new concepts. In a reversed cosmos, language would evolve backward. Words would grow more precise. Communication would tend toward clarity, reflecting the decreasing entropy of thought itself. Ambiguity would fade, not because beings become more intelligent, but because ambiguity is a high entropy phenomenon. As entropy falls, vagueness becomes less probable. Conversations would feel like recalling truths rather than exchanging information. Entire cultures might revolve around the idea that meaning is not created but uncovered, as though every mind is decoding a message written into the fabric of time. Decision-making becomes one of the most unusual aspects of consciousness under these conditions. In our universe, choices emerge from uncertainty. The future is wide open and decisions select one path from many. But in a universe moving toward a low entropy end, the future is fixed. Choices do not determine outcomes. Outcomes determine choices. A conscious being would not decide based on preference or prediction. The being would feel compelled by inevitability. Actions would not seem like branches in a tree of possibility. They would feel like stepping stones in a river that flows backward. The being might experience purpose not as aspiration, but as recognition. Every decision would be an act of aligning with what is already necessary. Despite this inversion, consciousness would not feel mechanical. It would feel alive, but differently structured. A mind would feel connected to something larger than itself, not because of mysticism, but because the low entropy future is shaping every particle, every neuron, every moment. Individuals might feel they are part of a single grand intention, that their lives are chords in a cosmic harmony, drawing all things toward final order. They would not worship the past. They would revere the future. Their myths would not tell stories of origin, but stories of conclusion. Their sciences would not study beginnings, but study the shape of the coming perfection. Yet, even in this reversed cosmos, consciousness would face challenges. Repulsive gravity ensures that no large-scale structures remain stable. Life, if it exists at all, must cling to fleeting conditions. Organisms would be transient, forming only because the decreasing entropy temporarily refines matter into life-supporting patterns. These organisms would disassemble as soon as the repulsive geometry of space stretches their environment apart. Life would be ephemeral. Minds would exist only in brief pockets where matter gathers into the delicately constrained forms needed for cognition. These pockets would not collapse. They would dissolve into finer and finer dust, not as decay, but as alignment with the disappearing degrees of freedom allowed by the future. Such beings might view death differently than we do. Death would not be the end of possibility. It would be the release of the individual into the tightening order of the cosmos. They might see dissolution not as loss, but as completion, as though the universe has recovered the information once housed in their minds and returned it to the narrowing reservoir of final clarity. What they call self might be more fluid than ours, because identity would be shaped by incoming constraints rather than by outgoing experiences. A mind in such a universe would feel itself changing, not because of encounters, but because the universe is continually refining what that mind must be. The self would be less a story and more a form of resonance with the cosmic future. To understand such consciousness fully, we must examine how physics models exotic forms of repulsion and negative mass, because even in our world, there exist hints, though faint and incomplete, of mechanisms that push rather than pull. This does not bring us closer to a reversed cosmos, but it reveals how our own laws stretch toward conceptual edges. And at those edges, we can see the difference between what our universe allows and what a reversed universe demands. To consider a universe where gravity repels instead of attracts, we must turn briefly to the version of physics we actually inhabit. Our cosmos knows attraction as the rule, yet in the far edges of theory, there exist rare hints of repulsive behavior. None of these phenomena produce true reversed gravity, and none of them resemble the sweeping divergence that shapes the reversed cosmos we have imagined. Still, these traces help reveal how tightly the laws of our universe are bound to their present form. They show that repulsion is not entirely forbidden, only profoundly restricted, confined to regimes where it cannot build structure or rewrite the cosmic script. These ideas do not open a doorway to a reversed universe, but they reveal the limits that the laws impose on such fantasies. One of the earliest clues comes from the concept of negative mass, a speculative idea in theoretical physics. Ordinary mass curves space inward. Negative mass would curve space outward. If such mass existed, it would behave in ways that defy ordinary intuition. It would accelerate in the opposite direction of applied forces. It would flee from ordinary mass while chasing other negative mass particles. The geometry around negative mass would resemble a local region of repulsive curvature. Yet real physics places strict limits on such exotic matter. Every attempt to incorporate negative mass into stable models leads to instabilities, runaway behavior, or violations of known energy conditions. These failures suggest that negative mass is not forbidden mathematically, but is incompatible with a universe that forms galaxies, stars, or even stable particles. It remains a ghost idea, haunting theory without ever manifesting in experiments. Next, there is the Casimir effect, a quantum mechanical phenomenon arising between closely spaced metal plates in a vacuum. The vacuum is not empty. It seethes with fluctuating fields. Between the plates, certain wavelengths are excluded, causing a subtle attraction. But under special conditions, this same physics can produce regions of negative energy density, tiny pockets where the local curvature of space behaves differently than expected. This negative energy is a faint whisper of what repulsive gravity might resemble, but it is so small and so fleeting that it cannot shape matter into large-scale forms. Quantum fluctuations that lower energy in one region are always accompanied by increases elsewhere, preserving the overall balance required for stability. These fluctuations reveal the pliability of space, but stop far short of reversing the universal arrow. Some of the most mysterious evidence for repulsion lies in the accelerating expansion of the universe. Distant galaxies are receding faster than expected from their mutual attraction. This acceleration suggests the presence of dark energy, a form of energy that fills space uniformly and produces a repulsive influence at cosmological scales. Dark energy does not push galaxies apart in the ordinary sense. It stretches space itself. The expansion is not an explosion but a geometric growth. This repulsive effect is real, measurable, and profound. Yet it is incredibly gentle. It does not tear apart stars or galaxies. it does not prevent structure from forming. It only becomes noticeable on the larger scales across billions of years. Dark energy is not reversed gravity. It is a background influence that coexists with attraction, allowing the universe to form structure before gradually pulling distant regions away from one another. These phenomena show that repulsion exists within the laws of physics, but only in limited forms. None of them create the kind of runaway divergence needed to prevent star formation or unbind galaxies instantly. None of them reverse the thermodynamic processes that govern cosmic evolution. They serve as reminders that gravity is not merely a force, but a geometric consequence of mass and energy. Altering that geometry requires extraordinary conditions, conditions that our universe does not supply. Attempts to imagine true anti-gravity often lead to frameworks such as ADS-CFT or higher dimensional models, where gravity emerges from deeper principles. These ideas help unify quantum theory with the curvature of space, but do not offer mechanisms for reversing gravity on demand. Even wormhole solutions, which require exotic matter with negative energy density, remain mathematical curiosities. They hover at the edges of possibility, never stabilizing into forms that could shape the universe at large. Every hint of repulsive behavior is restrained by deeper rules, as though the universe is willing to allow brief whispers of divergence, but refuses any sweeping rearrangement of its structure. This reluctance reveals something profound about the alignment between gravity and entropy. Gravity gathers matter into denser states. Entropy increases as these states release energy. Together they weave a consistent narrative of cosmic growth. If gravity were reversed, entropy would lose one of its strongest engines. If entropy were reversed, gravity would lose the conditions that allow collapse. Each arrow supports the other. Their alignment is not accidental. It is the deep equilibrium around which cosmic history is built. Understanding these subtle examples of repulsion in real physics allows us to appreciate how distant the reversed universe truly is. The laws we know cannot simply be flipped. Their symmetries allow mathematical reversal, but their physical boundary conditions anchor the arrows firmly. Yet even under these constraints, one domain allows tiny glimpses of entropy running backward. They are not large enough to reverse time or consciousness, but they reveal that decreasing entropy is not impossible, only improbable. These glimpses occur at the microscopic scale, where fluctuations can momentarily move in the direction that the universe normally forbids. To explore these rare events is to step closer to the edge of what thermodynamics allows in reality, and in doing so, to understand why global reversal is so utterly unreachable. The next chapter enters this microscopic realm, showing where entropy can briefly fall, why such events cannot accumulate into larger patterns, and what they reveal about the origins of time's arrow. The universe does not forbid entropy from decreasing. It only makes such events profoundly unlikely. At the smallest scales, where molecules dance in restless motion and quantum fluctuations stitch reality together moment by moment, entropy can slip in the opposite direction. These reversals do not violate any laws. They are woven into the same equations that govern the forward arrow of time. They are simply buried beneath overwhelming probabilities that prevent them from becoming visible in the world of stars, oceans, and living minds. Yet understanding these tiny exceptions helps us see why a global reversal of entropy is not only improbable, but incompatible with the universe's entire structure. Consider a small handful of gas molecules in an isolated box. If you wait long enough, there is a faint chance that all the molecules will spontaneously gather into one corner. This would represent a momentary decrease in entropy. The physics behind this possibility is simple. The molecules have no memory and follow straightforward motions governed by collisions and quantum forces. If enough collisions align just right, the improbable configuration appears. But the chance is so small that waiting the entire lifetime of the cosmos would not be sufficient to see it occur on any appreciable scale. These fluctuations do not break the second law of thermodynamics. They confirm it, for the second law does not ban decreases in entropy. It states only that increases are overwhelmingly favored. The mathematics behind these rare reversals has been captured in modern fluctuation theorems, such as the relations developed by Jarzynski and Crookes. These theorems quantify the likelihood of entropy decreasing in microscopic systems. They reveal that for very small energies and over very short times, entropy can indeed move backward. However, the theorems also show that as the system grows larger, or as timescales lengthen, the probability of such events becomes so tiny that it effectively vanishes. A drop in entropy that would be noticeable to the naked eye would require an orchestration of billions of trillions of microscopic reversals occurring at the same moment, an event so improbable that the universe could not produce it even if given lifetimes beyond imagination. Maxwell's demon, the famous thought experiment, tries to exploit microscopic fluctuations to decrease entropy. A tiny being opens and closes a door between two gas chambers, allowing fast molecules into one side and slow molecules into the other. By separating them, the demon reduces entropy. But the trap is subtle. To know which molecules to trap, the demon must gather information. Processing that information carries an unavoidable thermodynamic cost. When the full cycle is accounted for, the demon's actions increase entropy more than they reduce it. The thought experiment does not break the second law. It illuminates the deep connection between entropy and information. You cannot decrease entropy without paying the price in information processing, and that price always outweighs any gains. Quantum error correction offers another glimpse of temporary entropy reduction. In quantum systems, fragile states can be protected from decoherence by encoding the information across many particles. This reduces the effective entropy of the quantum state, yet the protection requires energy, measurement, and active intervention. The system as a whole produces more entropy than the local domain it protects. The global arrow remains untouched. The protection works only because an external agent continually spends energy, increasing entropy elsewhere. In nature, no such agent exists at cosmic scale. These microscopic reversals reveal that entropy is not a rigid command. It is a statistical preference. The arrow of time emerges because the universe started in a low entropy state. If the cosmos had begun in equilibrium, entropy would not have a direction. Microscopic reversals would occur as frequently as increases, producing a universe with no meaningful sense of past or future. But our world did not begin that way. It began in an astonishingly uniform configuration, one that contained immense potential for disorder, but very little disorder itself. That imbalance is the reason time has a direction at all. Without the low entropy beginning, the universe would be a sea of random fluctuations with no coherent history. To reverse entropy globally, you would need to replace this initial condition with its opposite. Instead of beginning in a low entropy state and moving toward higher entropy, the universe would need to begin in a high entropy state and evolve toward a low entropy one. But such a universe cannot produce stars or galaxies because gravity requires a low entropy beginning to generate structure. A smooth high entropy universe is one where matter is evenly spread out. With normal gravity, matter in such a universe would clump and increase entropy. With repulsive gravity, the clumping would never occur. Instead, the universe would race toward featureless smoothness. There is no path from a high entropy beginning to a low entropy end that resembles anything like the universe we know. Even if the laws allowed a reversed arrow, the boundary conditions do not. Thermodynamic laws reflect the past state of the cosmos more than they reflect the equations governing particles. Global entropy reversal contradicts the shape of the universe's initial condition. It contradicts the existence of structure. It contradicts the fundamental asymmetry encoded in every star, every galaxy, every breath of air. Microscopic reversals whisper that entropy does not command the universe. The initial condition does. and that condition cannot be changed without unmaking the entire architecture of cosmic history. These insights bring us back to the deep connection between entropy and gravity. Gravity amplifies entropy by creating environments where collapse releases energy. Entropy amplifies gravity by allowing structures to evolve irreversibly. If one arrow is reversed, the other becomes unstable. If both are reversed, the universe becomes something entirely different from ours. This leads us toward the final synthesis. The universe's arrows are not arbitrary. They exist because without them, the cosmos could not hold form, could not build structure, could not sustain evolution, and could not produce observers to ponder these questions. In the next and final chapter, we examine why the universe needs these arrows to remain aligned, and why their reversal is not merely dangerous, but logically incompatible with the reality we inhabit. The universe did not choose its arrows, it inherited them. Long before stars formed or atoms cooled, long before light separated from matter, the cosmos carried within it two guiding directions. One direction pointed toward increasing entropy, widening the space of possibilities with every moment. The other direction pointed toward gravitational structure, allowing matter to gather, collapse, ignite, and evolve. These arrows were not carved into the laws themselves. They were carved into the initial conditions, the very first arrangement of energy and matter from which everything else flowed. To understand why the universe needs these arrows is to understand why time moves at all, why stars shine, why galaxies form, and why minds can exist to contemplate these ideas. Without them, the cosmos would become a place without story, without change, without memory, and without the delicate architecture that makes meaning possible. In a universe with increasing entropy, time unfolds like a great river that broadens its banks as it flows. Each moment draws from a narrower set of microstates and pours into a wider one. This widening is the source of irreversibility. Once events occur, the universe cannot easily return to their earlier forms because the earlier states occupy such a tiny fraction of the available space. This asymmetry gives rise to sequences, histories, and causal chains. It allows life to gather experiences, to build memories, to adapt and evolve. If entropy did not increase, memories would have no direction. They would drift without anchoring. Identity itself would lose coherence, and awareness would dissolve into confusion. Entropy is not merely a measure of disorder. It is the scaffolding of temporal experience. Gravity provides the counterpoint, the sculptor that shapes form from the broad stage that entropy widens. Gravity takes the early smoothness of the cosmos and amplifies its subtle imperfections. What begins as a nearly featureless sea of particles evolves into clusters and filaments, into galaxies and stars, into planets that hold oceans of depth and atmospheres of breath. Gravity tightens the universe just enough to create pockets where entropy can flourish. These pockets become stars that burn, planets that cool, and ecosystems that grow. Gravity provides the stage on which entropy writes the script. Without gravity, the universe would be a mist of particles drifting into eternal dilution. Without entropy, the universe would be frozen in a timeless stillness, incapable of change. With both arrows aligned, the universe becomes a grand interplay of form and transformation. To reverse either arrow is to break this interplay. If entropy were reversed, the universe would not become orderly. It would lose its capacity for evolution. A world flowing from high entropy to low entropy would have no room for complexity to emerge. Every process would converge toward a predetermined future, and nothing truly new could appear. If gravity were reversed, the universe would not become free. It would lose its ability to build structure. Stars would never ignite, worlds would never coalesce, life would never arise. Reversing both arrows together yields not a mirror universe, but a cosmos stripped of narrative. Time would lose its flow. Structure would dissolve. Information would collapse into a state of tightening stasis. a universe approaching a final whisper rather than a symphony. This reveals a deep truth about why our universe works at all. The arrows create the tension needed for complexity. Entropy pushes outward, broadening possibilities. Gravity pulls inward, carving structure within that widening space. Between these two motions lies everything familiar. Stars exist because gravitational collapse increases entropy around them. Planets cool because heat diffuses outward while gravity keeps matter bound. Conscious minds arise because biological systems channel energy from concentrated sources into diffused sinks. Every breath, every storm, every beating heart is a negotiation between rising entropy and gravitational structure. The arrows are not rivals. They are partners, each providing what the other lacks. Even the cosmic expansion reflects this partnership. As the universe stretches, entropy grows by opening new states of arrangement. Gravity resists this growth locally, creating islands of structure within an ocean of expansion. These islands remain stable for billions of years, giving time the chance to sculpt life. When the expansion accelerates under dark energy, it does not erase the arrows, it extends them, allowing entropy to continue unfolding while gravity's architecture remains intact on smaller scales. The universe becomes a tapestry woven from opposing tendencies that balance each other with astonishing precision. This balance is not fragile. It is resilient because it arises from the deep boundary conditions that set the cosmos in motion. The early universe was hot, dense, and incredibly smooth. This smoothness is the signature of low gravitational entropy, a state far more ordered than any random arrangement of matter could ever achieve. From this order comes the possibility of collapse, the birth of stars, and the rich story of structure formation. From the heat comes the potential for diffusion, cooling, chemical gradients, and life. The arrows flow from the contrast between uniformity and energy, between stability and potential, between a simple beginning and a vast unfolding. To reverse the arrows is to reverse the meaning of that beginning. A high entropy start would give no room for structure. A repulsive gravitational geometry would offer no stage on which matter could collect. There would be no galaxies, no stars, no elements heavier than helium, no worlds where chemistry could explore itself, no organisms to observe the cosmos, and no consciousness to ponder the meaning of time. A reversed universe is not physically impossible. It is simply empty of story. It is a cosmos without becoming, a cosmos without emergence, a cosmos without observers, because nothing can take root in a world where possibilities collapse instead of expand. Our universe thrives because its arrows point forward. Entropy increases, giving time direction. Gravity attracts, giving matter purpose. Together they form the twin engines of cosmic evolution. They allow simplicity to blossom into complexity. They allow the cold to become warm and the warm to become radiant. They allow matter to ignite into stars that enrich the cosmos with heavy elements. They allow life to find footholds in the cooling surfaces of planets. They allow minds to awaken and wonder at their origins. The arrows do not simply exist, they enable existence. In the end, the universe does not ask whether its arrows could be reversed. It embodies the truth that their alignment is the reason there is anything to reverse at all. The cosmos moves forward because entropy demands it. Stars shine because gravity allows it. If either arrow turned back, the universe would not run in reverse. It would unravel into a place where nothing solidifies, nothing persists, and nothing remembers. The story of existence requires direction, and that direction is set by the arrows that guide the unfolding of time, structure, and meaning itself. The arrows of time and gravity do not simply guide change. They create the very conditions under which change can be recognized. Without entropy increasing, events would lose their sense of before and after. Every motion would appear reversible, every process symmetrical. A memory would not distinguish itself from an anticipation. A cause would not stand apart from an effect. The universe would lack the asymmetry needed for perception itself. In our world, awareness depends on the difference between what is stable and what is shifting, between what is recorded and what is yet to be experienced. These contrasts arise because the universe gives direction to its unfolding. The past is the archive of lower entropy states. The future is the frontier of higher entropy states. Consciousness builds itself upon this divide. Gravity deepens this divide by framing the scale on which entropy performs its work. It builds concentrations within which energy can flow and dissipate. A star is not merely a ball of burning gas. It is a gravitational engine that creates temperature gradients, pressure gradients, and steady transitions of matter into energy. These gradients feed the thermodynamic cycles that support chemistry and biology on distant planets. Without gravity, such gradients would be impossible. The cosmos would be nearly uniform in density and temperature, offering no foothold for life to develop its complex machinery of metabolism and thought. Entropy alone cannot make complexity. Gravity alone cannot ignite it. Together, they shape an environment rich enough for emergence. This partnership reveals itself in the simplest phenomena. A snowflake forms when water molecules lock into structured lattices under specific pressures and temperatures. This local increase in order requires the surrounding air to release heat, raising entropy overall. Gravity assists by guiding air currents, shaping clouds, and allowing large-scale patterns that create conditions for snowfall. Even a snowflake, delicate and ephemeral, reflects the deep alignment between entropy and gravity. The same alignment appears in mountain ranges uplifted by tectonic forces, in rivers carving valleys, in storms gathering over warm oceans. All these processes depend on gradients maintained by gravitational confinement and dissipated by entropy's relentless spread. At larger scales, the universe reveals the same pattern. Stars generate elements heavier than helium through nuclear fusion. These elements scatter through supernova explosions, enriching gas clouds that will one day form new stars and planets. The cycle repeats across billions of years. Each repetition increases the diversity of chemical possibilities. Gravity constructs the crucibles of fusion. Entropy disperses the products across space. Without either arrow, the cosmic cycle of enrichment would fail. There would be no carbon, no nitrogen, no oxygen, no iron. The building blocks of life would never appear. The complexity we see in living organisms is not a lucky accident, but a consequence of the universe, allowing its arrows to interact gently and continuously over immense stretches of time. Galaxies themselves are records of this interaction. Their formation begins with slight variations in density in the early universe. Gravity amplifies those variations until they form halos and filaments. Inside these structures, entropy increases through shock heating, star formation, and radiation. The galaxies then evolve into sprawling systems of hundreds of billions of stars. The spirals, bars, rings, and clusters are not random decorations. They are signatures of the long dialogue between gravity's shaping influence and entropy's expansive drift. If either process had been much stronger or much weaker, galaxies would not exhibit the breadth of structure we observe. The harmony between the arrows is delicate, yet robust. It is the architecture of cosmic evolution. Even the fragile emergence of life on planets like Earth depends on the arrows being aligned. Gravity holds atmospheres close, allowing climates to stabilize over long periods. Entropy drives biochemical reactions that convert sunlight into cellular energy. Organisms steadily increase their own order by exporting entropy into their environments. Every breath of oxygen, every pulse of heat in a living cell, every branching of a coral reef or spread of a forest represents the use of the arrows to build and maintain complexity against the constant drift toward equilibrium. Life is not a violation of the second law. It is an expression of the second law working through open systems. Life can flourish precisely because the universe keeps moving toward higher entropy while gravity maintains enough structure to support sustained flows of energy. The cosmos does not require life, yet the alignment of its arrows creates a universe where life is possible. The arrows do not guarantee intelligence, but they allow the formation of environments where intelligence can arise. Minds appear in planets that orbit stable stars, in ecosystems that recycle energy, in organisms that can gather information and store it in increasingly ordered forms. The ability to remember, to speculate, to imagine, to question the nature of time itself emerges from the tension between entropy and gravity. Consciousness sits at the junction of these arrows. Minds are time-bound because they track changes that depend on entropy. Minds are structured because gravity provides worlds stable enough for memory to persist. The arrows shape both the outer universe and the inner universe of thought. These insights show that the arrows are not optional details of physics. They are foundational conditions. Any significant reversal would destabilize the network of processes that allow complexity to grow. The arrows are intertwined threads in the cosmic tapestry. Pull one thread loose, and the entire weave unravels. A universe with reversed entropy might still obey the laws of motion, but it would lack the ability to evolve, create, or remember. A universe with reversed gravity might still allow particles to exist, but it would lack the ability to build structures on any scale. Reversing both arrows leaves a cosmos that is mathematically valid but devoid of the dynamics required for story, structure, or consciousness. The universe exists in the form we know not because it must, but because this form allows formation itself. It allows beginnings, middles, and ends. It allows stars to ignite and die. It allows matter to coalesce, break apart, reorganize, and try again. It allows energy to move from dense origins into diffuse futures. It allows time to have meaning. These are not small allowances. They are the conditions that make existence vibrant, changing, and rich enough to be understood. A universe without its arrows would be an eternal stillness. One with reversed arrows would be an eternal tightening. Only a universe with forward arrows can carry history. The universe holds its arrows not as burdens, but as freedoms. Entropy rising gives the cosmos a direction to expand its possibilities. Gravity attracting gives the cosmos a means to focus those possibilities into shapes that endure long enough to matter. Together they create tension, and from that tension arises every dynamic pattern the universe has ever known. If entropy were absent, nothing could change. If gravity were absent, nothing could gather. If both were reversed, nothing could mean anything at all. The arrows are not merely conditions of physics. They are the preconditions of significance. They allow the universe to host processes that unfold, structures that persist, and observers who witness themselves moving from moment to moment. This becomes clearer when we imagine trying to construct meaning in a universe without forward arrows. Meaning requires distinction between past and future. It requires stability on some scales and transformation on others. A reversible universe would erase this distinction. If every process could run equally well in either direction, memories would be indistinguishable from predictions. The mind could not anchor itself in an unfolding story. The world would appear like a mirrored hall of possibilities, each reflection identical, each direction identical. The sense of time passing would collapse. Awareness itself would dissolve into an ambiguity that no organism could survive. Life depends on asymmetry. Mind depends on asymmetry. Entropy supplies that asymmetry. Gravity supplies the other requirement. Without structure, there can be no stages on which events occur. Without density variations, there can be no stars or planets. Without stars, there can be no engines to drive the complex chemistry that life requires. Without planets, there can be no stable surfaces or atmospheres for life to emerge. The universe would be a fog of particles drifting apart. No organism could form a boundary between itself and its environment. No mind could anchor itself to a body. Consciousness requires a home. Gravity builds that home. When considering these requirements, the deep reason the arrows exist becomes apparent. They emerge from the simplest possible beginnings of the universe. A low entropy, nearly uniform early cosmos provides the seeds for both forward arrows. Its uniformity allows gravity to form structure. Its warmth and density allow entropy to flow outward. From that origin, stars, galaxies, planets, and life become possible. The universe does not need to push entropy upward. Its starting point simply gives entropy room to rise. It does not need to ensure gravity attracts. The curvature of space defined by its energy content does so naturally. The arrows arise effortlessly, and from them emerges everything not effortless. This alignment is not an accident. It is a necessity. If the early universe had begun in a high entropy state, its smoothness would not support gravitational collapse. No structure would form. The cosmos would be a dilute, ever-thinning mist. If it had begun in a chaotic and clumpy high-entropy state, gravity might create some small-scale structures, but the overall disorder would be so great that no large-scale patterns could hold. If it had begun with repulsive curvature, matter would have never gathered into anything at all. If it had begun cold and static, diffusion would not occur, and the universe would remain trapped in a state with no gradients, no flows, and no thermodynamic life. Only the actual initial condition, smooth enough for structure and energetic enough for change, produces the arrows that allow a story to unfold. Throughout cosmic time, the arrows of entropy and gravity have remained aligned. As gravity builds, entropy increases. As entropy increases, gravity creates the environments for that increase to accelerate. Planets form because stars form. Stars form because gas clouds collapse. Gas clouds collapse because gravity nudges them out of perfect balance. When stars die, they enrich the universe with heavier elements, which allow more complex chemistry and more intricate forms of matter. Every cycle of star birth and star death increases entropy. Every wave of collapse and dispersal engraves deeper structure into the universe. The arrows do not merely coexist, they intertwine. Their partnership creates the richness of cosmic evolution. If we imagine tampering with these arrows, even hypothetically, we come to appreciate their necessity. Reverse entropy, and time loses its meaning. Reverse gravity, and structure loses its possibility. Reverse both, and the universe becomes a place where nothing grows and nothing endures. Matter would drift into sharpening configurations while expanding away from itself. Time would collapse into a narrow funnel. No history could unfold. No life could arise. No mind could ask why the universe exists. The cosmos would still be a mathematical object, but not a living one. It would be a cold equation, not a story. By contrast, our universe is a story. It begins with simplicity and evolves into complexity. It begins with smoothness and evolves into stars and worlds. It begins with energy packed tightly and unfolds into galaxies spiraling like cosmic storms. It begins with a low entropy boundary and stretches forward into immense variety. Every moment adds to that variety. Every gravitational collapse and every thermodynamic diffusion writes another chapter. Each star that forms creates new possibilities. Each supernova seeds future worlds. Each planet gives matter a new stage on which to experiment. Each living organism reshapes the surface of its world. Each mind interprets the cosmos anew. None of this would exist without the arrows. Their alignment is not just a condition of physics. It is the quiet foundation that lets existence rise above emptiness. Entropy flows forward, opening possibilities. Gravity draws inward, shaping those possibilities into form. Between these motions lies the entire history of the universe. The stars shine because gravity allows them to collapse, and entropy allows them to radiate. Life breathes because energy can flow from concentration to dispersion. Minds think because time has direction. In this sense, the arrows are not simply features of the cosmos. They are the reasons the cosmos can host beings who wonder about its nature. When we look up at the night sky, we see not just scattered lights, but the visible signatures of these arrows at work. Each star is a monument to gravitational collapse and thermodynamic release. Each galaxy is a cathedral carved by time. Each breath we take carries the echo of the early universe expanding, cooling, and falling into patterns that allow chemistry, biology, and thought. The arrows shape the life we experience, the time we feel, and the meaning we create. If either arrow had pointed backward, none of this would have unfolded. If both had pointed backward, the universe would not just be different, it would be unmade. The existence of direction is the existence of possibility. The existence of structure is the existence of story. And because our universe possesses both, it possesses the capacity to reflect upon itself.